This is lessons 13.2, 13.4, and 13.5, stem and leaf plots, box and whisker plots, and histograms. So these are three different ways to visually represent a set of data. So first, the stem and leaf plot. One way to organize and display data is to use a stem and leaf plot. In a stem and leaf plot, numerical data are listed in ascending or descending order. So the stem is the greatest place value of the data, and then the leaves are the next greatest place value. And there's usually a key that shows you what the stem and leaf combination represents. So for example, the stem is a 2 and each of the leaves are, the stem represents 20 and each of the leaves are the units place value. So this is 20, 21, 21, 22, 23, and so on. So this is what a stem and leaf plot looks like. The nice thing about this is, again, they're in ascending or descending order, so it's easy to see, first of all, if there's any repeated numbers, so like 21 or 25. It's just easy to see how the data is distributed. Here there's a few more in the 20s than there are in the 30s or the 40s. So it's nice to be able to see that in a stem and leaf plot. So let's take a look at example 1. We want to display the data shown at the right in a stem and leaf plot. Okay, so the first thing I want to look at is see how, what sort of range we have for the data. So looking through here, I see numbers in the 50s, 60s, 70s, 80s, 90s, and that's it. So those will be my stems. So I have 50s, 60s, 70s, 80s, and 90s. Okay, and then remember these need to be in ascending order. So we'll start with a stem of 50, and I have two numbers there. I have 58 and 55. So 55 comes first, so our leaves will be 55 and 58. Notice you don't put commas between these, you're just listing the numbers. Okay, for the 60s, I have just 64, so that will just have one leaf of 4. For the 70s, just one at 75, so this will have a leaf of 5. And then there's a few in the 80s. So in order, we've got a couple 80s, so those are 2 leaves of 0. After that, we have an 85. And that's it for the 80s. Now the rest are all 90s. So the lowest one is 90, and then 92, and 95. Okay. And of course we want a key showing what the stem and leaves represent. It doesn't really matter which number you choose, so let's go with 85. So this key will show us that 8 as a stem and 5 as a leaf is equal to 85. So that is what a stem and leaf plot of this data would look like. So for the try it yourself problem, you're going to do basically the same thing. You're going to take this table over here and display it in a stem and leaf plot. So go ahead and pause the video and create that stem and leaf plot, and then when you're ready to check your answer, press play. Okay, so here's what your stem and leaf plot should look like for this one. Okay, and you should have chosen one of the numbers to use as your key. So I'll use 26, but this could have been a different number as long as you have some sort of a key showing what that represents. Okay, so those are basic stem and leaf plots. You can also have back-to-back stem and leaf plots. So a stem and leaf plot can be very useful for analyzing data since the values are organized and easy to see. A back-to-back stem and leaf plot compares two sets of data side by side, with the leaves for one set of data on one side of the stem and the leaves for the other set of data on the other side of the stem. So they really are back to back. So if we look at example 2, it It says the number of books read by students in an 11th grade and a 12th grade English class are shown. So here we see, just to kind of make sure this makes sense, here's the zero stem. So for 11th grade, these numbers represent 5, 6, 7, and 8. In 12th grade, these represent 3, 6, and 8. Now in the 10 stem, this is 12, 13, 14, 15, 15, 17, 17. So think of this as kind of being a mirror image of what you would be used to seeing normally from a stem and leaf plot. And then on the other side, this is like normal. This is 13, 13, 16, 17, 18. So the leaves are still the same, they're just put on the other side of the stem. So if we want to find the median of each set of data, that's the nice thing about a stem and leaf plot is that because the numbers are ordered, it's very easy to find where the median is located. So let's look at the 11th grade. We have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers, which means that the median would be right in the middle of that, or the 8th number, because that would split it into 7 on each side. So, but you want to make sure when you're counting that you're counting them in order. So we'd start from the smallest one, 1, 2, 3, 4, and then keep going. The next biggest one would be here, 5, 6, 7, 8. So this has a stem of 1 and a leaf of 5. So for 11th grade, the median is 15. All right, let's do the same thing for 12th grade. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers. So again, the median will be at the 8th number, right in the middle. So 1, 2, 3, 4, 5, 6, 7, 8. So that has a stem of 1 and a leaf of 8. So for the 12th grade, that would be 18. So which grade has read a more varied number of books? Well, we want to know which one is more varied, which one has more variation in the number. Well, if we look at the 11th grade, they're all clustered, not all, but a large majority of them are clustered on this same stem. Whereas 12th grade, you can see there's a little more variety, looking for more varied. There's a little more variety in the selection of numbers. So, so here we would say the 12th grade is more varied. Because 11th grade is clustered at the 10 stem. Okay. So for the try it yourself problems, you're going to use the same back-to-back stem and leaf plot to answer 2 more questions. So pause the video and answer those 2 questions. When you're ready to check your answers, press play. Okay, for the first one, all this is asking you for is the range, the difference between the least number of books and the most number of books. So for 11th grade, the range is 31. And for 12th grade, the range is 36. And for the second one, in general, which class read the most books? If you look at the distribution of the data, 12th grade has more numbers that are on the higher stems. So they have the same number of numbers that are on the 30 stem, but 12th grade has more in the 20 stem, and 11th grade has more in the 0 stem and in the 10 stem. So because there's numbers higher in the higher stems in the 12th grade, we would say in general the 12th grade read the most books. So this would be 12th grade. Okay, so those are stem and leaf plots. We're going to move on to a different way of visually representing data, and that is a box and whisker plot. So a box and whisker plot divides a set of data into 4 parts using the median and quartiles. So we saw these in section 13.3 where we found the median, the upper and lower quartiles. So that's what we use for a box and whisker plot. Each of these parts contains 25% of the data. So this section here that goes from the lowest or least, the lowest extreme or least value up to the lower quartile represents 25% or 1/4 of the data. The section from the lower quartile to the median represents another 25% or 1/4 of the data. Same from the median to the upper quartile, that's another 25%, and then the upper quartile to the upper extreme or the greatest value is another 25%. So this is, box and whisker plot is really good for showing how spread out the data is, because you can see just how big of a gap there is in each quarter. All right, so let's see what these look like. Okay, so example 3 says to construct a box and whisker plot for the data shown. And you'll probably recognize this data. This is the exact same data that we used in the section, the notes for section 13.3. So just to save a little time so that we don't have to completely redo finding the median and the two quartiles, we're just going to use the information that we already had from that lesson. So what we did was we first put the numbers in order. Just a refresher, we put the numbers in order. We found that the median was 5. And then we found the median of the upper half, which is the lower or the upper quartile. Let me fix that. We found the median of the upper half, so that's the upper quartile. And for that set, we got 7. And remember, this was all done in section 13.3. So if this isn't sounding familiar, you can look back at your notes for that section. The lower quartile, we found the median of the lower half, and that was 3. So the only other numbers we need in order to make our box and whisker plot are the lowest value and the highest value. So we can look back at our ordered list from section 13.3, or we can look at this table. The lowest value is 2.5. And then the highest value is our outlier at 14. Okay, so to make a box and whisker plot, you'll notice in the picture here that a box and whisker plot is lined up against a number line, because if you want this to actually be representative for how spread out the data is, it needs to have some sort of set interval. So we do want to make sure that we are drawing this right next to a number line. So we will start by drawing a number line. And notice our numbers need to go from 2.5 to 14. So we'll just have them go from 2 to 14 because we want them to be a unit each. So we'll start, leave a little bit of room to actually draw the box and whisker plot. We'll go ahead and draw a number line. And even though we will put a mark for each number, you don't necessarily have to label each and every one. I'm just going to label every 2. And you want to try to draw them with as consistent of intervals as you can. It won't be perfect, but it should be close. Okay, and we only need to go up to 14, so that's all the more number line that I need. Okay, so now we just want to mark points above the number line, not on the number line, but above it for where these 5 special points go. So the low value is at 2.5. That's right here. The lower quartile was at 3. That's right there. The median was at 5. That's right there. Upper quartile at 7. And then the high at 14. Okay, and we'll connect all of these with a line. Wait, just kidding. We don't want to connect those with a line. We only want the whiskers to have a line. Sorry about that. We want to draw a box around the middle ones. So draw vertical line segments to make the box. And this is around the 3 middle ones. So you'll have 1 dot to the left still and 1 dot to the right. So we want our box to look like this. So the middle line is the median and the lines on either end are the upper and lower quartiles. Then we'll draw a line, and it's just the whiskers. So here's the lower quarter of the data, and here's the upper quarter of the data. So now you can see, because we already looked at this set of data, this should help make this a little more clear, hopefully. Remember, we talked about this being an outlier because it was too far outside of the interquartile range. Well, here you can see the interquartile range is just within this box. And this is very clearly pretty far away from this range. So this is the nice thing about a box and whisker plot, is that you can see how spread out the data is. So right here between the low value and the lower quartile, there's not much variation at all. Within the box, in that middle half of the data, the second 25% and the third 25%, there's not a whole lot. It's more varied than this is for sure because it's wider, but it's not a whole lot of variety. But then you have this big gap here to get to the high value, and that suggests that this is most likely an outlier. One thing you should notice though about a box and whisker plot is that if you were to just look at this, you cannot tell anything about the individual data points or how many of them there are. So the only thing, sorry about that, the only thing that I can tell from looking at a box and whisker plot is that a quarter of the data is in this section here, a quarter of the data is in this section here, a quarter here, and a quarter here. You don't know the individual numbers for each one though. Okay, so this just kind of repeats what I just said. Although the four parts of a box and whisker plot may differ in length, each part still represents 1/4 or 25% of the data. A longer whisker or box shows the data have a greater range. A shorter whisker or box shows the data are more closely grouped together. So in the next example, we'll actually interpret some data that is displayed in a box and whisker plot. So it says the price of computers in dollars at Electronics Town and Best Purchase are shown in the box and whisker plots below. So we've got two box and whisker plots lined up against the same number line. One represents one store, one represents the other. The first question asks, what percent of computers at Electronics Town cost less than $325? Now remember, we don't know anything about the individual data points here, but we do know something about the percentages in each section. So we'll look at 325, and we're looking at Electronics Town. So go up to Electronics Town, and we find that this point at 325 is the lower quartile. And we want to know how many cost less than this. Well, that would be just this one section here. Remember, each section represents 25%, so that would just be 25%. For question B, what percent of computers at Best Purchase cost less than $940? So we'll find 940, go up to Best Purchase, and we all know how many cost less than this. Well, that's one section, two sections, three sections, and they are each 25%. So 25, 50, 75%. Okay, and then the last one, how does the price of computers at Electronics Town compare to the price of computers at Best Purchase? Well, again, you don't have the individual data points, but what you should be able to see is just where the spread is. So notice their lowest computers cost the same amount, but Electronics Town highest price computer is the same cost as Best Purchase's middle priced computer, meaning that half, this whole section here, half of the computers at Best Purchase cost more than the most expensive computer at Electronics Town. So that would be a good comparison to make between those, is that this whole half of the cost at Best Purchase, this whole half of the computers cost more than all of the other ones at Electronics Town. So we could say that half of the computers at, I'm just going to abbreviate Best Purchase as BP, cost more than the most expensive computer at Electronics Town. Okay, so the try-it-yourself problem is similar. You have a box and whisker plot comparing the heights of basketball players on two different teams, and they're plotted together along the same number line. So take a couple minutes and answer those three questions, pause the video, and when you're ready to check your answers, press play. Okay, the first one, what percent of the ravens are 70 inches or taller? That would be 75%. What percent of the lancers are 75 inches or taller? That would be 50%. And then how do the heights of the ravens compare to the heights of the lancers? Well, you'll notice the middle is the exact same. The median for both sets of data is the exact same. But the lancers don't have a whole lot of variety in their heights. They're very clustered. So the boxes are narrow, the whiskers are narrow, whereas the ravens are a little more spread out. So we can't really compare, we couldn't say that the ravens are taller or that they're shorter because half of the lancers are spread in this area and half of the ravens are spread in this area. So the tallest raven is definitely taller than the tallest lancer, but you can't say that the ravens are taller because look, they have shorter people than the lancers do too. So the one easy to make comparison here is that the height of um, the Ravens basketball players is more varied than the height of the Lancers players. And that's not the only conclusion you could make here, but that's a pretty easy one to spot. So we would say the heights of the Ravens are more varied. You could also say that both teams have half of the players 75 inches or taller or 75 inches or smaller. Either way, notice basically saying that they both have the same median. That would be another observation you could make. Okay, so the last thing that we have to look at, last way to display data, is with a histogram. A histogram uses bars to display numerical data that have been organized into equal intervals. So histograms look like bar graphs, but they're not because they're along the horizontal axis. These are intervals. So it's basically something that's used to represent the frequency of something. There's no space between bars. That's how you can tell the difference between, well, one of the ways anyway, the difference between a histogram and a bar graph. Because the intervals are equal, and this is very important that the intervals have to be equal, all of the bars have the same width so that it gives you that visual of um, which intervals have the most number of data points. Intervals with a frequency of 0 have no bar. It's still on the graph because it's still an interval and you'd still need that space there, but it would just not have a bar. Okay, so let's do one of these together. Example 5 says the frequency table shows the highest elevations in each state. Display the data in a histogram. So sometimes a frequency table is a little confusing to understand how exactly this came about. So the idea here is that um, somebody went through and started going through one state at a time. So, pick a state and figured out what the highest elevation was in that state and then classified it into one of these categories. So let's say we started with Texas and I have no idea, but let's say the highest elevation in Texas is 13,000 feet. Well, that would give us somewhere between this range and that would give us one tally mark in that category. And somebody did the same thing for all the other states so that we now have this frequency table. So this is the number of states that fall into each of these intervals. So we're going to put this information on our histogram. So notice on the horizontal axis, the x-axis, we have each of those intervals and they're equally spaced. Notice the numbers are also equally spaced. Each bar is about 4,000 feet, 3,999, but you get the idea. Notice it's the same gap here, same gap here, same gap here, and so on. So those intervals have to be the same size. Because a histogram represents a frequency, this will always be number of something, whatever it is that you're counting. So in this case, each tally mark represents a state, so this is the number of states. Okay, so let's go ahead and create our histogram. So for the first interval, the frequency is 22. So the bar for this should go up to 22. Okay, and then we'd color that in. Okay, the second interval from 4,000 to 7,999 has a frequency of 14. So this bar would go up to 14. Okay, we'd color that bar in. In the next category, 8,000 to 11,999, the frequency is only 2, so this bar will only go up to 2. Okay, the next interval has a frequency of 11, so we would go all the way up to 11. And then color that in. The next interval has a frequency of 0, so we'll just leave this like it is. We can't draw any sort of a bar because if we have any sort of height to it, it represents more than 0. So we just leave this part blank to show that there's nothing in this interval, but we still have to have it there to show that this is not the next interval right after this one. This one has just 1 as its frequency, so this will be a very small bar. Okay. So, nice things about a histogram. First of all, you can see somewhat how varied the data are. So we see that it's very, very common for the highest elevation in the state to be not very high at all. Um, and then from there, we kind of have this, what looks like maybe an outlier. We're not for sure because we don't know the exact numbers and we haven't calculated the interquartile range or anything like that. But this looks like it might be an outlier. It looks a lot higher than the rest of these. So again, like a box and whisker plot, you can't see the individual data points in a histogram, but you can see how common certain intervals are. So that is one good thing about a histogram. Okay, so for the try it yourself problem, you are going to create a histogram. So you have a blank graph here to work from. Don't forget to put a title and label the X and Y axis with whatever is appropriate for this particular problem. So pause the video and then take a few minutes to create that histogram, and when you're ready to check your answer, press play to continue. Okay, so this is what your histogram should look like for the try it yourself problem. The title should be water park admission, or you could say cost of water park admission, but it's obvious that cost is involved, so you wouldn't need that there. And then number of parks, remember this is always the things that you are counting. And then we've already had the intervals created for us, so we really just had to create each of the bars. So that's what your histogram should look like for try it yourself number 5. Okay, last page. Here we're actually going to interpret histograms. And again, you cannot see the individual data points in a histogram, but you can still answer questions about how many data points are in each category. So the histogram at the right shows the number of hits the student websites in Miss Foster's computer class get in a day. So that's what we see in this histogram, hits in thousands from 0 on up to 6. Now notice here that the way these intervals are marked is not quite the same as the one on the previous page. This is a different way of labeling this. So this shows with the 1 here at this line between the two bars, this shows that this interval goes from 0 to 1, and that's how many um, how many websites got between 0 and 1,000 hits. This interval is from 1,000 to 2,000, so this is the number that were between 1,000 and 2,000, and so on. So we want to know how many websites received 2,999 or less hits. Well, this is really close to 3,000, so we would be looking at 3,000 and then to the left, so all the way down. So let's see how many we're looking at. Here for this bar, that's 4. For this bar, that's 5. And for this one, 8. So how many websites? 4 plus 5 plus 8, which is 17 websites. Okay, so let's take a look at um, question B. It says, what percent of websites receive 5,000 or more hits? Now, if you recall, in order to calculate a percent, we need to know the number that received 5,000 or more hits, and then also the total number. So if we're looking at 5,000 or more, that's at this interval right here, and more would be to the right. So we're just looking at this single interval from 5 to 6,000, and that has a height of 2. So we know our percent will be 2 out of something. So now we need to actually add up each of the bars to know how many there are total. So we'd have 4 plus 5 plus 8 plus 9 plus 3 plus the 2. Don't forget to count this in the total. So if we add these together, 4 plus 5 is 9, 9 plus 8 is 17, 17 plus 9 is 26, plus 3 more is 29, plus 2 is 31. So this is 2 out of 31. And if you recall, to change this to a percent, we can just divide. 2 divided by 31, and that comes out to approximately 6.5%. Okay. For the try it yourself problem, you're going to interpret a pair of histograms and answer some questions about that. So pause the video and work through those few questions, and when you're ready to check your answers, press play. Okay, the first one, how many days did each city receive 12 or more inches of snow? Well, for Toronto, that was 14 days. And for Seattle, it was only 9 days. How many more days did Toronto receive 18 or more inches of snow than Seattle? So we'd want to find the number of days that Toronto received 18 or more inches, and then the number of days that Seattle received 18 more inches, and figure out what the difference is between them. So you should have gotten that Toronto had 11 days minus Seattle, which had 5, which gives you a difference of 6 more days. Okay. And the last one, what was the greatest amount of snowfall for each city? Well, this is kind of a trick question because all we can tell from the histogram, remember you can't see individual data points, all we know is that there's two days where the inches of snow was between 28 and 36. So we could definitely say that it was at least 28 and less than 36, but we don't know where. And again, that's 2 different days, so that could have been 2 different amounts. Um, we just know it's between 28 and 36. Same thing here. This has a height of 3, so there were 3 days where the inches of snow were between those 2 numbers, but we don't know where in between. It could be closer to 28, it could be very close to 36, we don't know. So this question is actually, again, kind of a trick question. The greatest amount of snowfall for each city, all we can say is that it was between 28 and 36 inches. Okay, and that is it for the 3 representations of data that we're going to talk about in this chapter. So part of what we'll look at in class is just kind of the benefits of each one, what you can easily see from some versus others, and when you might want to use one over another to represent a set of data.